Good morning, everyone. Um, I am Manuel Bravo. I'm from the University Argentina of Chile. And this work is with other university, with the geophysics department from the University of Concepcion, the University of Católica Santísima Concepción, and University Andrés Bello from Chile. This is titled GNSS Based Detection of Ionospheric Disturbance Associated with Earthquake, Tsunami, and Volcanic Eruption, but this specifically in South America region. Earthquake, tsunami, and volcanic eruption generate atmospheric acoustic gravity waves that propagate upward and disturb the ionosphere. The disturbance can be remotely detected using GNSS observation. You can observe the co-seismic, co-tsunamic ionospheric disturbance that, depending the velocity, you can observe it 8 minutes after the earthquake, the acoustic wave, and approximately 45 minutes after the earthquake, the gravity wave, and possibly induced by tsunami. Also, volcanic eruption can produce a strong ionospheric disturbance through the generation of the acoustic and gravity waves also. Acoustic and gravity waves are distinguished by characteristic frequency and period change and velocities. But what is the ionosphere? The ionosphere is a partially ionized region of the upper atmosphere located mainly within the upper mesosphere and thermosphere. It contains the free electron and ions that affect radio wave propagation and GNSS signals. GNSS dual frequency observation allow the estimation of the total electron content, TEC or tech variation. The TEC is the electron density integrated along a beam between the bottom and the top of the ionosphere. Tech variation, in this case, we can be used to monitor ionospheric disturbance traveling generated by natural hazards. GNSS tech detection methodology. Then we use the GNSS observation. For this, we use the RINEX file from the IGS, the RINEX file from the Centro Sismológico Nacional from Chile, the RAMSAT network from Argentina, the RBMC from Brazil, and the LISN from Peru. For the tech estimation, we use the Gopi-Semala method. And for the training and filtering the wave, we use the 10th order Polynomial field and baseband filtering between 0.5 and 5 millihertz. That this is a standard filtering used for other authors before. This is a one image for plot for the filtering. And we can see the 3 times over the South American map, and that you can see the disturbance travel from the epicenter of the earthquake, that is the red star. In the map, you can see travel disturbance from the star, from the epicenter, and for this is better used one special plot called odochrome. Odochrome is a travel time plot that is very easy obtain the velocity because it's the slope of this plot. And you can see the range of the distance, or when starting after of the earthquake. The result. We observed traveling ionospheric disturbance, or TID. We considered the event in South America only between 2010 and 2020 were selected considering only earthquakes with magnitude greater than 6.7 and volcanic eruption with index greater than 2. This resulted in a database with 63 earthquakes and 20 volcanic eruptions. This is the table of the 63 earthquakes where only TID observed when you have the 7 column, the satellite. This is the continuation of the table. And this is the table of the volcanic eruption, where only 2 TID are observed. Then, for 63 earthquakes, only 10 earthquakes corresponding is observed on a TID, and only 2 volcanic eruptions we observe on a TID. Some characteristics of this earthquake. For example, only in one time we observed a fast perturbation, possibly associated with Rayleigh surface waves, together a characteristic acoustic wave signature in the panel A. In the panel B, we can see the resonant ionospheric disturbance. This is associated with the volcano eruption Calbuco in 2015. In the panel C, we can see the acoustic and one gravity wave may be associated with a tsunami. And also here we can artifacts related to method of Semala that is visible due to the UT date transition. And in the last plot, in the plot D, we can see a weird ionospheric signature associated with the 2014 Easter Island earthquake event, likely due to sparse nerve degeneration coverage. Other characteristic of this earthquake, that in the first row, we can see the same ionospheric disturbance, but observed to the north, in the left, in the right, revealing predominant northward propagation in the southern hemispheres related to upward propagation along geomagnetic field lines. In the bottom row, panel C and D show another event where no clear disturbance is observed in the east, and the left panel, while a weak signature is detected at the west, possibly associated with the filtering in Andes Mountains. Another analysis with this TID or waves is the wavelet analysis. In this case, we can see the resonant TID in the eruption of volcano Calbuco in 2015, show resonant oscillation with dominant periodicity centered around 200 seconds. In the right panel, we can see the acoustic wave exhibit dominant periodicity centered around the 300 seconds, consistent with the acoustic gravity wave dynamics. When we do a regression analysis of the ionospheric disturbance parameters, we can see that there are some thresholds. For example, in the left, depth versus magnitude show that tech disturbance are mainly observed for events with magnitude greater than 7, while affect events are generally shallower than 40 kilometers. In the right panel is latitude versus magnitude of the earthquake. Here showed that the events associated with TC disturbance are located to north to 45 degrees south, of latitude. And in this other plot, TAD amplitude versus magnitude of the earthquake show an approximately linear relationship for the acoustic wave component, while the gravity wave trend that is represented with asterisks is less certain due to the limit number point. Of the 63 events, we only observed 10 events with TID associated to acoustic wave, and only these 3 points that are represented with asterisk is gravity waves. And in the right panel, TID amplitude versus depth show no clear relationship between them. In TID amplitude versus propagation range, suggesting that larger amplitude disturbance tend to propagate over gradient distance in the left panel, in the left plot. And in the right plot, latitude versus magnetic inclination show no clear association of the TID occurrence or amplitude. I want to mention that of the 3 cases of the gravity waves induced by tsunami, the asterisk, in other words, my student compared with the virtual tide gauge with the delta tech. And in some case, for example, in the bottom is in the first hour is a good agreement between the virtual tie and this disturbance with the gravity waves in the tech. In other case, upper is not clear the agreement. Also, I want to mention that this disturbance we can observe in the ionozone. For example, in the first row in Jicamarca, we observe an intermediary layer during the earthquake in Peru in 2013, and in bottom in Tucumán, ionozone, we can observe an additional stratification that with agreement of the time of the paths of the TID. Then, GNSS derived by TEC observation successfully detect ionospheric disturbance associated with earthquake, tsunami, and volcanic eruption in South America in the near field. Detected traveling ionospheric disturbance, or TID, exhibit propagation patterns consistent with atmospheric acoustic gravity wave dynamics with characteristic spectral periodicity and velocities also. A magnitude threshold, magnitude greater than 7, and focal depth constraint typical shallower than 40 kilometers are generally required for clear ionospheric detectable in South America. This is very important because it's only in this characteristic is only in regional location. However, some events that exceeding this magnitude no produce detectable TID when occurring a larger depth, highlighting the strong control of the focal depth on the lithosphere atmosphere-ionosphere coupling. Among the events satisfies both magnitude greater than 7 and depth less than 40 kilometers, most corresponding to strike slip faulting, and are predominantly located in the Scotia Plate region, that is the orange oval, suggesting a possible tectonic control on ionospheric coupling efficiency. And TID amplitude show a clear linear relationship with the earthquake magnitude and increase with the propagation rate, indicating a systematic scaling of the ionospheric disturbance when event energy and spatial extent. 5 of the 10 earthquakes associated TID cases identified in this work, in this study, has been previously reported. And both volcanic eruption cases reported in this studio is reported before. This is consistent with early documented ionospheric response, supporting the robustly to the response of the ionosphere. Thank you.